Let me know when you're ready to
Hi
roll.
Maya, how are you? And today we are here. Welcome back to another episode of the Tech Simplified Podcast, and where we break down complex tech into simple stories. I'm your host, Riz Life, and today's episode is deep dive into the most exciting and fast-growing field in the world, machine learning, and also known as ML. Did you know machine learning is a subset of artificial intelligence and that allows computers to learn from data without being explicitly programmed. So
Ooh,
my first question is it's about training algorithm to identify patterns, make decisions, and even predict future outcomes. So instead of
that's
writing
a
step-by-step code, we feed the machine with the data and it learns the logic from the data. So,
that's right. Let it
uh,
figure it out.
what do you think about?
It's fascinating, isn't it? Like teaching a puppy a trick, but with numbers instead of treats. So, what are some of the kinds of things people are using machine learning for these days? Hello?
Yeah,
Are we still connected?
yeah. Start. Okay, give me what's the difference between AI, ML, and deep learning?
Ooh, good question. People throw those terms around like they're interchangeable, but there are some key differences. Think of it like this: AI is the big umbrella term, right? It's all about making machines smart. ML is a specific type of AI. It's like one of the branches under that big umbrella. It focuses on teaching computers to learn from data, just like we talked about with the puppy and the treats. Deep learning is like the fancy PhD student of ML. It's a subset of ML that uses artificial neural networks with lots and lots of layers, mimicking how our brains work. Those layers allow it to learn really complex patterns and relationships in data. Does that make sense?
Exactly. So what is a data set and machine learning?
Good question. Think of a data set like a giant buffet for a machine learning algorithm. It's a collection of information, could be numbers, text, images, sounds, all organized and ready for the algorithm to dig into. Imagine a machine learning algorithm wanting to learn about different kinds of dogs. The data set would be filled with pictures of dogs labeled with their breeds. The algorithm would analyze those pictures, finding patterns and features that define a pug, a chihuahua, a golden retriever, and so on. The more data it has, the better it gets at recognizing different breeds.
Great. What do you mean by training a model?
Training a model is like teaching a dog a new trick. You show it examples, the data set, and reward it when it gets things right. Is this with machine learning instead of treats? We use something called a loss function. It's like a scorecard that tells us how well the model is doing. We feed the data to the model and it makes predictions. If it's wrong, the loss function gives it a low score. The model then adjusts its internal settings, a bit like tweaking the way it understands the information to try and get a better score next time. We repeat this process over and over with lots and lots of data until the model gets really good at making accurate predictions. Does that make sense?
Great. What is overfitting and underfitting?
Great question. You're really digging into the nitty gritty. Think of it like this. Imagine you're teaching a kid to identify apples. You only show them red, round apples. They learn apple means red and round. Then you show them a green apple. They say, that's not an apple. That's overfitting. The model learned the training data too well, but can't generalize to new examples. Now, imagine you show the kid a bunch of random fruits and say, these are apples. But be clueless. That's underfitting. The model is too simple to capture the patterns in the data. The goal is to find that sweet spot in the middle, where the model understands the important features but can still adapt to new information. It's like teaching the kid to identify apples by their shape, color, and even a little sniff.
Okay, great. What is the difference between classification and regression?
Oh, I love these distinctions. Think of them like two different types of questions you can ask a machine learning model. Classification is like asking, is this a cat or a dog? It's about putting things into categories. Regression is like asking, how much will this house sell for? And it's about predicting a continuous value. So if you're building a system to identify spam emails, you'd use classification. If you're building a system to predict stock prices, you'd use regression. Got it?
Yeah, great. What is the role of features and labels in machine learning?
Ah, features and labels, the power couple of machine learning. Think of it like this. You're trying to teach a computer to recognize pictures of different fruits. The features are like the clues the computer uses to identify the fruit. Think of things like, is it round or oval? What color is it? Does it have a stem? You'd feed these features into the model. The labels are the answers, the truth the model is trying to learn. So if the picture is of an apple, the label would be apple. The model learns by figuring out which features are most important for predicting the correct label. So does that make sense?
Exactly. Uh, how do you evaluate machine learning models' performance and what is cross-validation?
Good question. It's not enough to just build a model. We need to know if it actually works. That's where evaluation comes in. It's like giving the model a pop quiz to see what it's learned. We use different metrics depending on what kind of model we're dealing with. For classification, we might look at accuracy. How often does it get the right answer? For regression, we might look at mean squared error. How far off are its predictions on average? Cross-validation is a cool trick to make sure our model isn't just memorizing the training data like a parrot. We split our data into several chunks. We train the model on some chunks and test it on the rest. We repeat this process using different combinations of chunks and average the results. It gives us a more reliable estimate of how well the model will perform on new, unseen data.
Okay, great.
Is everything all right?
What are precisions, recall, and F1 score?
Ah, those are important. Think of them like three judges giving a performance review to our machine learning model, but each judge has different priorities. Precision is like the accuracy judge. It's focused on making sure the model only makes positive predictions when it's truly confident. It asks, out of all the times the model said yes, how many were actually correct? Recall, on the other hand, is like the thoroughness judge. It cares about catching every single instance of the thing we're looking for. It asks, out of all the actual yeses cases, how many did the model manage to find? The F1 score is like the compromise judge. It tries to balance precision and recall. It's a single score that summarizes how well the model is doing overall. Think of it like a detective solving a case. Precision is like making sure every arrest is legitimate. Recall is making sure no guilty suspects slip through the cracks. The F1 score is finding the sweet spot between being too cautious and too eager.
Great. What are some common machine learning algorithms and when do we use them?
Great question. We're getting into the toolbox now. There are tons of machine learning algorithms out there, each with its own strengths and weaknesses. It's like choosing the right tool for the job. Here are a few common ones, and when they shine, linear regression. Imagine trying to draw a straight line through a bunch of data points. This is great for predicting a continuous value when there's a clear linear relationship between the input and output. Logistic regression. This one's like deciding if a student will pass or fail an exam based on their study time. It's used for binary classification problems, predicting one of two outcomes. decision trees. Think of it like a flow chart, asking a series of yes no questions to make a decision. These are versatile and easy to understand, but can get complex with lots of features. Support vector machines. Imagine finding the best line that separates two groups of data points as cleanly as possible. These are
Hello? Okay, Maya, what's the difference between batch learning and online learning?
are powerful for classification, especially when data is complex. Neural networks. This is the brain inspired approach with lots of interconnected nodes mimicking neurons. Great for complex tasks like image recognition and natural language processing. That's just a taste. There's a whole world of algorithms out there.
Okay, Maya, listen, my next question is what is the difference between batch learning and online learning?
Ooh, you're diving deep into the technicalities. Here's the breakdown. Imagine two different ways of teaching a puppy a new trick. Batch learning is like a classroom full of puppies who have a fixed set of examples, all ready to go. You walk through each example with the puppies, showing them the trick and giving them treats when they get it right. Then, after going through all the examples, you assess the puppy's performance. It's efficient for large data sets, but not so great if new examples keep popping up. Online learning is like teaching the puppy one trick at a time. Imagine you show the puppy the trick, reward them if they get it right, and then move on to the next example. The puppy is continually learning and adjusting as they encounter new data. It's more adaptable to new information, but can be slower than batch learning for very large data sets. There are pros and cons to both approaches.
Okay,
It
great.
really depends on the situation
Now
and the
we are diving into advanced industry use questions. How do you handle imbalanced data sets?
the infamous imbalanced data set. Imagine trying to teach a model to detect a rare disease that only affects a tiny percentage of the population. If your data set is mostly healthy folks, the model might just learn to say healthy all the time and miss the rare cases. So, what can we do? Think of it like
What
boosting the voice.
Okay, what are feature engineering and feature selection?
We're tackling some really important topics now. Let's break it down. Think of your data as raw ingredients. Feature engineering and feature selection are like the prepping in choosing the best ingredients to make a delicious meal. Here's the rundown. Feature engineering. This is like turning boring old vegetables into a flavorful stir fry. You take your raw data and transform it into something more useful for your machine learning model. This could mean creating new features from existing ones. For example, if you have data on customer purchases, you could engineer a total spending feature by adding up all their purchases, transforming data into a different format. Maybe you have text data. You could use techniques like bag of words to represent it as a numerical vector that the model can understand. Feature selection. This is like choosing which spices to add to your dish. You have tons of features, but not all of them are equally important. Feature selection helps you pick the most relevant ones for your model, which can improve performance. Using only the most important features can make the model more accurate and efficient. Prevent overfitting. Too many features can confuse the model, leading to overfitting. Make the model more interpretable. Having a smaller set of features can make it easier to understand how the model makes its predictions. Think of it like this. Both feature engineering and feature selection are essential for turning your raw data into a delicious machine learning feast.
Great. What's the role of hyperparameters in training ML models?
That's a great question. Hyperparameters are like the settings on your oven. They control how your machine learning model learns from data. Just like you need the right temperature and time for a cake to bake perfectly, you need the right hyperparameters for your model to perform its best. Think of it this way. You have your data, which is like the ingredients for your cake. You have your model, which is like the recipe. Hyperparameters are like the oven temperature and baking time. Choosing the right hyperparameters can make the difference between a fluffy, delicious cake and a burnt, inedible mess. Here are some examples of hyperparameters. Learning rate. This controls how big of a step the model takes when adjusting its internal settings. Too big and it might overshoot the target. Too small and it might take forever to learn. Number of layers in a neural network. This determines the model's complexity. More layers can capture more complex patterns, but too many can lead to overfitting. Finding the optimal hyperparameters is often a bit of a trial and error process, like experimenting with different oven settings to bake the perfect cake. There are techniques like grid search and cross-validation that can help you systematically explore different combinations and find the best set for your particular problem.
Great.
Are you still
Okay.
there?
How do you choose the right algorithms for a task? And what is the impact of data quality in machine learning performance?
I'm really thinking deep thoughts now. Choosing the right algorithm is like picking the right tool for a job. Think about fixing a leaky faucet. You wouldn't use air, would you? You'd use a wrench. Here's what you consider the type of task. Classification. Predicting categories like spam or not spam. That calls for algorithms like logistic regression, support vector machines, or decision trees. Regression, predicting a continuous value like house prices. You'd look into linear regression or more complex methods like neural networks. Size and quality of your data. Small data set. Simpler algorithms might be best to prevent overfitting. Lots of data? Go wild with more complex models. Interpretability. Need to explain how your model works? Decision trees are pretty transparent. Neural networks are like a black box, harder to interpret. Data quality is huge. Imagine you're training a model to identify dogs in pictures, but half the pictures are blurry or just random objects. Your model will be confused and perform poorly. Garbage in, garbage out. Here's how data quality impacts things. Accuracy, junk data, and accurate predictions. Bias data leads to biased models, perpetuating unfairness. Reliability. Inconsistent data will lead to unreliable results. It boils down to understanding your problem, knowing your data, and choosing an algorithm that's a good fit.
Okay. Now, machine
You're doing
learning
fantastic.
is not just a buzzword. It's shaping our lives every day. Whether you're a student and developer, business owner, understanding ML can give you a major edge in today's digital world. So thanks for tuning in today's episode. If you liked, do not forget to like and comment or subscribe to our channel. You can follow me on Instagram, Spotify for more content. And Maya, thank
Don't
you very much for being here. We will catch you in the next episode. Thank you, greatness.
You got it. Always a pleasure, Maya. Can't wait to chat again soon.
Thank you, greatness.